Um, it
Yes,
has, yes, it has started.
so let me begin. I think we are on
Yeah,
time.
yeah.
Okay, hello, good evening to all of you. Let me begin by welcoming you all for this ISC TIFR webinar series. So me and my colleague, Professor Jyotisman Das Gupta and TIFR Mumbai have started a special joint ISC TIFR webinar series. And one of the objective of this webinar series is to keep the student community intellectually engaged and strive for academic excellence. So this new series of virtual seminars will bring international experts in various subfields of chemical sciences, which are closer to the students and faculties of TIFR and IISc. These are the two top research institutes in the country. So the hope is here is that we will invite a leading international experts to deliver two talks once in a month, and we actually learn the subject complexities and forefront research ideas in a scholarly manner. So these are all tutorial type talks. So you are welcome to interrupt the speaker, ask questions, and clarify your ideas and doubts. And today we are indeed fortunate to have with us Professor Ned Sibert, one of the leading experts in a vibrational spectroscopy. Professor Sibert, welcome to virtual seminar series to IISc and TIFR. So before I hand over to Jayshree to formally introduce Professor Ned Sibert, I would like to thank ACS, in particular Ajay Zha and Diksha, for sponsoring this webinar series through ACS Talks. So Jayshree, you may introduce Professor Sibert.
Thank you, Satish. Hello, everyone. My name is Jayshree Nagesh, and I'm a Ramanujan Faculty Fellow at IISc. It's indeed a pleasure and a privilege for me to introduce my PhD advisor and theoretical chemist, Professor Edwin Sibert, from the University of Wisconsin-Madison today as a speaker in the IISc TIFR webinar series in chemical sciences. I have to say that it's almost impossible to get Ned to travel to India. And trust me, Amber Sai and I have actually tried, and I'm so glad that we have him here today online. So Ned completed his bachelor's from Colgate University in US in 1978 and went on to obtain his PhD degree at University of Colorado Boulder in 1983, also in US, jointly under the supervision of Professor William P. Reinhardt and Professor James T. Hines in chemical physics. He then had a short stint of postdoctoral experience at Oxford with Professor Mark Child as a NATO fellow and a Miller fellow at Berkeley with Professor William Miller before moving to Madison in 1986. Ned's research areas involved developing theories to describe the nuclear dynamics and spectroscopy of small to medium-sized molecules, both in gas and condensed phases. These include elucidating proton transfer reactions, photodissociation of hydrogen bonded molecules, vibration relaxation mechanisms, non-adiabatic vibrational dynamics involving multiple potential energy surfaces, and I should say an often less talked topic close to his heart, which is to understand chaotic behavior and vibrations. Well, anyway, all in all, if you want to learn anything in molecular vibrations, he's the person to go to. Ned is an exceptional teacher and can explain difficult concepts using just the right examples. This is true both at the level of undergraduate education and during personal discussions. This is no surprise, and this is reflected in several teaching awards he has received, including the UW-Madison Chancellor's Award, Teaching Excellence Award, and James Taylor Excellence in Teaching Award at the Chemistry Department in Madison. As a PhD student, I always walked away from our personal discussions with a feeling of awe and had to make sure to write down things immediately after our meetings so as to not forget his exact words, the way he explained certain things. I'm excited to see and listen to Ned. And so without further ado, let's all get ready to learn about molecular vibrations in the first part of his talks titled Vibrational Spectroscopy Beyond the Harmonic Approximation. Ned?
Jayshree, thank you very much for those kind words and putting a little pressure on me. These talks that I'm giving are really designed for students. So I ask all the students to pretend that the professors and older people in the room really don't exist. And I'm trying to connect with you and talk to you. And I've designed a lecture, first one I'm giving, that is really covering the basics. Before I start though, I want to just give you a quick snapshot of Madison. It's pretty cold, whether you're in centigrade or Fahrenheit. But in February, it warms up. We get to go play on the ice and have festivals. And then in March, the sporting starts. We don't have cricket on the ice, but we have fishing. And then in April, we start breaking up the ice because we want to get out there and start swimming. Now, then it gets beautiful. And we have gorgeous, gorgeous weather. Already now, I saw people in shorts this morning as I walked down the street before this talk. We have a beautiful student union. Madison is surrounded by lakes. It's got beautiful buildings, a wonderful campus. And our chemistry building is ever growing. This doesn't show the new wing, but this is our chemistry building. And I picked this one because you can actually see the lake in the background. So Madison is pretty close to Chicago. Everyone knows where Chicago is, so I don't ever try to go any further than that. And having done that introduction, I'm now going to step back and start talking about vibrations. I think every talk on vibrations has to start with the harmonic oscillator. It's what you first learn about in your first physics course. And maybe I have the equation written a little differently here because instead of a 1 over a mass, I have a Wilson G matrix element. The G's are common things that people use in vibrations. And the basic idea is that once you've done the Born-Oppenheimer approximation, you've solved the electronic equation, you basically get a problem that's equivalent to 2 balls coupled by a spring. And when you have that kind of a model, the simplest thing is you have this quadratic potential, just a 1/2 kx squared. And then the motion on this is a simple oscillatory sine or cosine type motion. And the important thing in this particular oscillator is that the frequencies are independent of the energy. The way you would say this in quantum mechanics is that the energy levels that you solve for are equally spaced. And so the energy it takes to go from the 0 to 1 level or the 1 to 2 level or the 2 to 3 level, it's all the same. And basically selection rules that are based on the dipole moment that I won't talk about much today tell you it's easiest to go from 0 to 1 or 1 to 2 or 2 to 3, depending on where your initial population is. Now, this model of atoms lasted until about 1930, and then it got replaced by the Morse oscillator. The Morse oscillator has the important feature that when you extend the bond, basically it breaks. You have a dissociation energy. And this very simple functional form, where here is the dissociation energy, allows you to describe vibrations in a very sophisticated way. And it's one of the go-to models for molecular vibrations. And this particular model, it has the harmonic part, but then it has the extra part over here that tells you that the energy levels are getting closer and closer. And you see that in this picture as you climb up this manifold of states, the energy levels are getting closer and closer together. And that turns out in the classical world is telling you that the classical frequency down here is one value. And if you put more energy in the molecule, the classical frequency is changing. So the Morse oscillator tells you that the energy and frequency are intimately connected. And the more energy you have, the lower the frequency. And one of the things I'm going to keep stressing on this talk is that we always want to be considering 2 things, frequencies and couplings. This model quickly gets surpassed, if you want to get to anything more sophisticated, by actually allowing 2 springs to couple. And so in this particular model, there is no coupling because I have an X degree of freedom, I have a Y degree of freedom, so my Hamiltonian sum, so you don't expect any kind of interaction. And I'm starting here so you can see what the uncoupled picture looks like. And when you go to multiple dimensions, you always have a problem representing your potential. And here we're doing it with equipotential contours. So each of these lines corresponds to a constant energy. And if I move along this red line, basically I'm moving along this particular direction. And the way you read this is, it's like a topographical map. Here is a valley. You're walking down into the valley, and then you're slowly walking back up the other side. And so if I could take a cut along that red line, I would just get the curve to the left. Now, this is the case where there's no coupling. And this is what you get when you actually solve this problem. You get something that looks like a box. And the reason you get something that looks like a box is because your classical trajectory is oscillating back and forth. You've got much more energy in the y degree of freedom. And because they're uncoupled, I always get to the same amplitude in the y and the same amplitude in the x. And so this is a classical trajectory. They make these beautiful Lissajous figures. And it's whenever you see a box, it tells you that there doesn't seem to be any coupling. And because it's aligned with the axes of the figure, it means there's no coupling in the x and the y degrees of freedom. So in this particular case, I've ignored this term. I've set it equal to 0. In reality, every time this oscillator extends, if you think in the center of mass frame, this atom, the central atom, moves, and it causes this bond to contract. So an extension of this bond causes this bond to get smaller, and that leads to a kinetic coupling. The size of this coupling is going to depend on the mass of this object. Also, there is potential coupling, and I've just chosen not to include it in this particular model. And that potential coupling would tell you that if you extend this oscillator a little bit, there'll be some restoring force. But that restoring force is going to change when you pull this particular spring, because really these aren't springs. They're electrons that we're trying to model with springs. And so the forces would change as I increase this bond length. So this is just a very simple two-dimensional model, but let's add just a touch of coupling. The instant I add any coupling, even though this number is very small, that box rotates at 45 degrees. What we have here is a symmetric stretch and an asymmetric stretch. And these are the normal modes of the molecule. And so this is what you're taught very early on. You have these normal modes. And basically all you're doing when you go to a normal mode representation, you're just going from the x and the y coordinates to a new set of coordinates. And all you've done is a rotation. And so now this box looks just like the box in the original picture. And so even though my modes are coupled in this picture, down here they seem to be uncoupled. And so I got this beautiful box. So normal modes allow us to decouple molecular vibrations at low energies. The only difference between this particular picture and this particular picture is in this particular picture, I've chosen to run the trajectory longer. So you don't get to see any white space inside that box. And I have most of the energy in the asymmetric stretch. And so you can see that these are nice tight boxes that correspond to excitation in different modes. And this is all in a classical perspective. And in this one, you see I put excitation in both modes. You will note that it no longer looks like a simple box. And that's because these are really Morse oscillators. And there is little tiny bits of couplings that deform these boxes. But to a good approximation, this looks like a box. When talking to students, one of the really hard things is when you don't see their faces, you don't know whether they're browsing the internet or whether they're looking perplexed. And so any questions that you might have would really help guide me and help keep you engaged in this talk. So let's look at some other coupling situations, because these simple models contain a tremendous amount of information. Here's a case where I now have different masses, and so my springs have different frequencies. And now when I add a coupling, basically my box still stays moving in the up and down position. These coordinates, to a good approximation, are uncoupled. There's only a slight rotation you need of this box to get it to lie along the x, get it to lie perpendicular to the axis. And so when you have an energy mismatch of your two oscillators, and you can see omega-1 is much greater here, that's the x, it's because it's oscillating many times as it goes up and then many times as it comes back down. And so even though there's a coupling, that coupling doesn't have an important role.
Sorry
Next
about that,
box.
Ned. Sorry about that. Somebody
Okay,
got
that's no
unmuted.
problem.
Yeah.
The next box, it's an interesting case. I've chosen some coupling, so it's -3/5. And you get a trajectory that looks like this. And here, this is omega A is approximately 2 omega S. And in this simple figure, basically the energy is still staying the same in the asymmetric stretch, because that's this direction, and it keeps just repeating itself. And what you see is every time I go 1/2 step in this direction, the asymmetric stretch does a full vibration. So that's that 2-to-1 ratio. If I simply switch the coupling, instead of having it be -3/5, I make it +3/5, then omega S is equal to 2 omega A. Then you get a completely different picture. It's prettier. And there's no kind of rotation that one can do that would get this picture so it looked like a box. And so normal modes are not enough. In certain instances, we have to go beyond that simple normal mode perspective. Moreover, as you go to higher energies, all I'm doing here is I'm keeping the parameters the same, but I'm increasing the energy. And one of the things you see is that it starts to look a little bit noisier. And then when you get to even higher energies, you get something that looks like spaghetti. And if you look at if you try to follow one of these trajectories, follow the line. So basically what I'm plotting here is X and Y as a function of time. Starts off and goes up and down. It's got all the energy in the Y degree of freedom. But at some time later, it has all the energy in the other degree of freedom, in the X degree of freedom. So here, in this particular one, at higher energies, all of our simple pictures have broken down.
Ned, there is a question.
Okay.
Hi. So,
Yeah, it's Watsal.
yeah. So, can you please go to the previous slide?
Yes.
So, can you please explain the difference between the second and the third graph? I mean, what physically changed because of which there's a change in this graph?
That is a great question. And I'm going to ask you to answer that question later on in the talk. So I put this up, I put these two pictures up to pique your curiosity, get you to think about this. And so I'm really, really excited you thought about it. You're going to have to wait. But what you should be thinking about is what is fundamentally different about this particular picture, where I have this one being twice this one, and this one where it's twice that one. And all I've done is I've changed these mass factors.
Okay.
We'll get to that. That is an incredible, what is the difference?
Okay.
Thanks for asking that.
AD, can I ask a question?
Yes, please. Yes, please, Sanjay.
Ned, this is Sanjay.
Hi, Sanjay.
Usually the symmetric stretches are smaller than the antisymmetric stretches. So in which situation you would expect the WS to be twice the WA?
If you are, you know more than you should. You are right. And this is a simple model problem. And one of these is pretty unphysical. And in fact, this one is unphysical because I said this kind of coupling right here, it has to deal with the fact that when one bond extends, the other one contracts. And in a linear molecule, that is always the case. And so the asymmetric stretch is almost always higher than the symmetric stretch. And you would have to get to a bond angle under 90 degrees, which of course you don't often see, where one stretch would cause the other stretch to increase. So you know too much. You are right. And this is unphysical. And one could imagine a case where you had potential couplings like this, but this is just a model. So don't take it too seriously.
Okay, thank you.
It's another great question.
Can I ask a question?
Yes.
So this a negative sign for the coupling constant, what does it mean?
What it means is what it means in this, what it means in the spring picture, what it means is when this bond extends, it causes this bond to contract.
Okay.
Now, a really nice one, if this is 90 degrees right here,
Mhm.
you know what the value of this would be?
So obviously that will not couple.
So in other words, if I have a right angle
Mhm.
in a molecule,
Yeah.
and this is all for very small displacement, so slight increase in this bond, how would it cause this bond to increase or decrease?
So that will not have any effect, right?
That's right. And so there are angles where this coupling goes to zero.
Yeah.
And so this thing, it depends on angles and it depends on masses.
Okay. But what about the sign?
See, the sign?
Yeah.
The sign is telling me that when this bond extends, this one contracts. So that's the sign.
Okay.
And that's why if the angle here is less than 90 degrees, this becomes positive. Basically, this has a cosine term in it.
Okay.
And so these things are simple geometrical functions of angles and bond lengths. And there's this book called Wilson, Decius, and Cross that tells you how you can calculate these kinds of parameters.
Thank you. Thank you, Neil.
So here I was. All I did here is I went to higher energies. And this actually is good news because at higher energies, and Fermi recognized this early on when he coupled a bunch of anharmonic oscillators, is that you get to have statistical theories. And that instead of asking about the details of an individual trajectory, you could just realize that this trajectory is filling up all of the available so-called phase space. But it just travels everywhere it can possibly travel. And so this is a chaotic trajectory, and it is something that's beyond my lectures. But it turns out that at low energies, you have normal modes. Slightly higher energies, you're going to see some of these resonant type interactions, but that at high enough energies, everything falls apart and becomes statistical. And we're always trying to learn something new as we climb up that energy ladder, because as you get these new behaviors, they're revealed in interesting ways through molecular spectroscopy. I'm going to switch here to a different Hamiltonian. This is a normal mode Hamiltonian. And when you do a normal mode Hamiltonian, one of the things you do is you do rotations that get rid of those couplings between the momentum. So people like these because there's no more of a P1, P2 term. You've done it by rotating your coordinates to get rid of it. And so I have just two oscillators here, K1 and K2. And I'm going to add a cubic coupling. So this is, instead of having that Morse problem where it was hard to see what kind of resonances might be at play, I'm writing down the coupling in a very specific way to illustrate how these coupling mechanisms come into play. And I'm going to pick up a simple case. I pick these two. So notice these there's no rotation here. And there's no rotation because these have different frequencies and this coupling is pretty small. If I change, excuse me?
Sorry, I request all the attendees and panelists to please mute themselves unless you're asking a question. Thank you very much. Carry on.
I always forget to do that myself.
That's carry on.
One of the things one way to analyze this in that
JD, can I
classical
interrupt
world.
one more time?
Yes,
Sure.
please, Sanjay, ask the question.
Ned, what is K sub 122?
K122 this is a coupling term that I am adding. And so basically, when one has a potential energy surface, the lowest order approximation is to assume that it is harmonic in both those degrees of freedom. But really, the potential has various different terms. And so what you could imagine a term like this is telling you is that as you're stretching bond 1,
Okay.
this term would lead to an extra quadratic term that is changing the force constant for mode 2.
Okay.
And you can imagine that molecules have these kinds of terms in them. You know, as you like stretch a something like a CH stretch, and you keep pulling on that CH stretch, pulling on that CH stretch, the bond's getting weaker and weaker, and you expect the bend force constant to progressively get weaker as you increase the length of that CH bond. And so I'm treating this as a simple model Hamiltonian, but this is a kind of term that, you know, it would describe that kind of an interaction.
Does this mean anything that you have raised the x2 to the power 2, but not the x1?
That is an excellent question. We're going to see the answer to that really quickly.
Okay.
That is, you're going to see the answer to that in about 2 minutes. One can define the energy. So one can write down an expression. If you're solving Newton's equations of motions, something like this is about a 6-line program in MATLAB. You know this value, you know this value, so you could plot the energy in each of these modes as functions of time. And this is what you see. Now, if I change the frequency,
hello.
Can
in
I?
this particular case,
Yes, this is Kunal here. So, want to ask the second term is k1 x1 square plus k2. It would be, I think, x2 square.
Yeah, that's a typographical error, I think.
Yeah.
Yeah, it's just an x2, right?
Thank you.
K2 x2 square.
That's K1.
And the parameters. Just the pure Hamiltonian, you said half k1 x1 square plus k2 x2 square. I think that's just a typo.
Okay.
Yeah.
And,
Okay.
Ned, I have a question.
Yes.
So in all these plots, your red curves, do I understand it's the flow of energy in a vibrational multidimensional vibrational surface?
Can you speak a little bit more loudly?
These red lines in all these plots, do I visualize it as a flow of vibrational energy in a multidimensional potential energy surface?
Yes. And so let me show you this picture.
Okay.
So what we're showing in these trajectories is, follow this guy. Actually, it starts off about here and goes back and forth, back and forth. And so basically all the energy is in X1. Eventually, after some time, all the energy is in this degree of freedom. The way you can describe that information is by looking at the energy in those two modes. And so what you see as a function of time, you have two oscillators. And energy is flowing out of oscillator number 1 and flowing in to oscillator number 2. And so then the question is, well, it must be this term, because if that term's not there, nothing happens. So why is it that this particular term is causing all of this energy to flow?
But my question is, why does it become chaotic for high energies?
You have to ask for Hari that question. And the key to it is, and I'll come back and talk about this in just a little later.
Okay, thank you.
I'm sort of building this up at this low energy. What we have is a resonance. And I have set up the K1 and K2 values so that I have a 2-to-1 resonance between my two modes. And so that is a key thing called a Fermi resonance, and I'm going to talk about it a little bit more. But if one were to try to go further, one of the things I was saying before is that In real systems, as energy flows between various different degrees of freedom, their frequencies tend to adjust. And so you have a resonance like this is causing energy to flow fastly between these 2 degrees of freedom. And eventually what can happen is it finds another kind of resonance, maybe a 2 to 3 resonance or something like that. And when you get too many of these things, you start to get chaos. These resonances are important from a spectroscopic point of view, because oftentimes one mode is the mode that you can excite with your laser. It's the one that has intensity, it's the one that carries oscillator strength. And so without a resonance, when you're doing vibrational spectroscopy, you could only excite certain modes. But if energy can then flow from one mode to another, basically somehow there must be a spectroscopic signature that's telling you that you're exploring different parts of that potential energy surface. Now that seems more like a quantum mechanical statement. So let me do a comparison of classical and quantum mechanics. This is what you get for the same Hamiltonian when you solve and get the classical dynamics. Essentially, this is an uncoupled picture. Basically, you have lots of energy in the x degree of freedom, or in this case, you have an oscillator with like 9 quantum of excitation in the x1 degree of freedom. And if you go, if you go in this direction, it looks like a simple Gaussian. So this would correspond to the ground state oscillator for x2. This would be like a simple Gaussian in the x2 degree of freedom, times a highly excited vibrational state in the x1 degree of freedom. And as you probably, I don't know when you last thought about it, but one knows that when one solves quantum mechanics, one can take and solve for time-dependent states. So one can imagine a state, like a zero-order state that corresponds to 9 quanta of excitation in mode x1. This would be a zero-order state. And then what one does is to solve for the time dependence of a state, you just expand it in terms of its eigenfunctions and multiply it by the phase factor. So solving for the time dependence of eigenstates is really trivial if you can solve for the eigenfunctions of my Schrodinger equation. And the only difference here is this is just a Hamiltonian for mode 1. And when you do that, you get a picture that looks like this. It's pretty similar. The pictures on the right and the left are pretty similar. The one on the right shows less energy flow. It doesn't have those small oscillations, but the pictures are pretty similar. Let's compare that to the second case. In the second case, you can see that when the classical mechanics has a resonance, the quantum mechanics does something very different. The shapes of these things appears to be fairly similar. And when one has energy flow, one can see that just like you have classical energy flow, when there is a resonance in quantum mechanics, it's causing energy flow between the various degrees of freedom. So this is a time-dependent view of spectroscopy. That when you have this resonance, energy flows. So let me explain why this happens. If you look at the energy levels, you get a picture that looks like this. This is a funny case where I have this perfect 2-to-1 resonance. And so this would correspond to 1 quanta in mode 2. And then here I've got 2 states that are coupled. So it's 2 quanta in mode 2 or 1 quanta in mode 1. And actually you get whole sets of states that look like this that are isoenergetic. In other words, I could take 1 quanta out of mode 1 and put it in, decrease it so it goes from 3 to 2. But the isoenergetic state, I have to take 0 quanta here and put 2 quanta here. So this is the 2-to-1 resonance. And the way you can convey this information is basically all these red dots. Now each red dot here corresponds to a 0-order state. So a 0-order state that has 3 quanta in mode 1 and 0 in mode 2 is just this dot right here. And then the next dot is this dot. And the blue line corresponds to mostly equal potential. All these states are going to have about the same energy. So what's happening, energy still has to be conserved, total energy. And the coupling can only hold so much energy. So basically, if you're going to have energy flow, it's going to mostly move along this particular line. Now, why did I pick the coupling in this form? This is what Fermi recognized. The beauty, and this is something I'll come back to, when I have a product state here, and I have a direct product, and here I have product form of a coupling, and this is another direct product state. What one can do is break this two-dimensional integral into two one-dimensional integrals. This is key to writing these things down. And when one does that, the one-dimensional integral that you have here has a linear harmonic oscillator term that's coupling the 3 to the 2. And we know from our harmonic oscillator selection rules that x1 leads to a delta V equals 1 transition. And so this is the kind of matrix element that we expect to be non-zero. Likewise, we need the quadratic term here because this leads to delta V equals 0 or 2. In this particular case, this term is just the kind of term that allows the 0 state to couple to the 2 state. So this coupling term is specifically designed to couple the 3, 0 to the 2, 1. What I did is I added a term that allowed mixing this energy to flow back and forth between these two states. So the two requirements were there. I had to have nearly degenerate states, and I had to have them coupled. What one can do is, in a quantum mechanical sense, one can think about what's going on. And in a quantum mechanical sense, I could look at the overlap between my initial state, that's this state, with all the other zero order states as a function of time. And so basically what I'm going to do is I'm going to be taking my initial state, which was the 1, and I'm going to evolve it as a function of time. And so if I start off time t equals 0, the overlap with the initial state is 1, and it just dies off exponentially and then slowly comes back. And then we believe in causality, and so what happens is energy would go from here to here, and so probability moves up first in this one, and then a little later the probability moves up in this one, and at the end it moves up into this state. And then it goes back and forth and back and forth. And so there's this probability flow along this manifold of states. The amazing thing is, and this is something Heller really pushed, and I'll talk about this some more, is that the spectrum is basically the Fourier transform of the overlap of the initial wave function with itself as a function of time. So except for the fact that I've squared it here, encoded in this decay function here and then its recurrence is all the information I need to get this particular spectrum. So there's an intimate connection between energy flowing in this direction and then returning and this spectrum. And that's something I'm going to talk a little bit more about.
Yeah, Ned, just a quick question from Vatsal, and then I might have a question. So Vatsal, could you?
Yeah, can you please go to the previous slide? Yeah, so does the molecule spend equal amounts of time in all these degenerate states, or is there any preference statistically with time? In which state is there any preference?
Yes, there is, and it depends subtly on lots of things. But this, in the experiment, what you control is you get to pick the initial state. And so I picked this particular initial state. But I could have picked any other initial state. I could have picked this state, I could have picked this state, I could have picked some linear combination of these states. And at these low energies, things are not statistical. And so energy is not completely equally shared between all of these levels in the example that I'm showing you. And it tends to prefer a couple, some more than others. And there's sort of technical reasons for that, and it has to do with the symmetry of the problem that I've done. But yeah, it's not completely shared even along this manifold. So what this resonance has done is it's opened up a pathway for energy flow. Initially, without that coupling, you're stuck on a red dot. You turn on that coupling and it now allows you a passage to move along that blue line. And that's the coupling that leads to the spectrum. And I haven't said more about that, but you do not statistically get to travel equally amongst all of those red dots on that blue curve. That's a good question.
And that just the connection to the probability and the spectrum that you have, it seems very similar to the absorption spectrum, right? When we calculate absorption spectrum going from ground state to excited states, and looking at all the Fourier, all the Frank-Condon overlap terms, and something similar to what Lee and Heller did when they compared it to resonance Raman process. One is the autocorrelation, and the other is some sort of a sort of a cross correlation between two different vibronic or vibrational states in the ground and the excited potential. It almost looks like that, right? The mathematics of it.
Yes, and you'll see that picture in a minute.
Okay.
Yeah. I have a question for you guys. Let me add this picture. The amount of mixing depends on the frequencies and couplings. So what is the key difference between these two results? This is a bit tricky. It's a bit subtle in this particular question. I've written down over here what the couplings have to be. So in this particular case, you want this coupling. And in this particular case, you would want that coupling. You see how when you're looking at resonances, and you see a 2-to-1 resonance, there's always a coupling associated with those resonances based on the arguments that I took you through. Where did I go? Based on the arguments I gave you right here. So it's because of this particular form, that x1, x2, and these matrix elements, this having to be a delta V equals 1, and this having to be a delta V equals 2, that this works. Does anyone have any ideas why? And let me be more careful to say, this is the asymmetric stretch, and this is the symmetric stretch. This is the asymmetric squared, and this is the symmetric stretch. This was that initial model that I gave you. This is where symmetry comes into play. Symmetry has some important features. What it is you can't have terms like this in your Hamiltonian, because whether you move in the positive or the negative direction along the asymmetric stretch, it can't possibly affect the shape of the potential. You can see that just by looking at the picture. Whether I move to the left or the right on the asymmetric stretch, I get the exact same picture. And so the potential must be symmetric with respect to the asymmetric stretch. This is an odd term. It can't exist. So this will never happen. And so in our Morse potential, if you had expanded it out and looked for that term, it wouldn't exist. And so that's why, even though you could have a perfect 2-to-1 resonance, sometimes there is no evidence of mixing because of symmetry.
Ned, just a small question.
Yes.
In one case, so if you look at the potential terms, it is, if you look at it is kx cube, it's a cubic, because it is
Those are both
to
cubic terms.
Yeah, these are cubic terms.
So in other words, if I took that initial Morse potential and Taylor series expanded it,
Yeah.
What I would find is there would never be a term. This term can't exist because the potential has a mirror plane of symmetry. If I draw a diagonal down here,
Okay.
There's a mirror plane of symmetry, and the potential on this side is equivalent to the potential on that side. So that's why I can't have that term there.
Okay.
Was that the question?
No, I was just looking at dimensionally because Hooke's law potential are square terms, right?
Say that one more time.
No, generally potential is a square, it's a kx square or something like that.
Yeah.
But this year you have it is a cube.
Yes.
So why is it so?
Let me and you could imagine one can Taylor series expand this potential.
Okay.
And when one Taylor series expands this potential, you know, in the initial coordinates, it's just a Morse coordinate in x1 and a Morse coordinate in x2.
Okay.
So basically, what you get when you expand the potential and you go beyond the quadratic expansion, there's going to be a term x cubed.
Yeah.
And there's going to be another term y cubed.
Yeah.
And what you'll find is that the force constant for the x cubed and y cubed, those two terms have to be the same.
Yeah.
But when you then rotate those into the normal coordinates and say, well, going all the way back here,
But what happens to the initial terms?
so this originally this was an x cubed and I had x cubed and y cubed, but when you write them in terms of these coordinates,
Yeah.
what you find is that you will get a term. There'll be an s cubed term and there'll be a squared term, and that's it. So because of symmetry, those are the only two terms when you write the x cubed plus y cubed. And so when you do that simple expansion, this term is just never there.
So what are the other terms go to zero? The initial terms?
Oh, you mean the quadratic terms?
Yeah. The first
So
few
They're
terms,
still
They're still there.
they're still there.
yeah. So these, I'm just right here. I'm not saying this is the total potential. This is just the extra coupling term that you might have in addition. I didn't understand your question. In addition to the quadratic terms,
Oh, okay.
there is still the x squared and the y squared. They're really important. The x squared and the y squared, they're what telling us they set up these basic frequencies.
Okay.
These terms are what are sort of tickling that basic picture and adding and causing little bits of energy flow to take place.
Right.
And so basically what we're thinking about is the influence of these terms, the addition of these terms, or what these terms might do when you have the initial case. So this is still the coupled Morse potential. I haven't changed the potential.
Right.
Just if I Taylor series it and look at the lowest order terms, this is what I would find.
Sure. Yeah, and I think the terms, the complete Hamiltonian is still, it has the square terms, plus you have this coupling term. So that's what the idea. And so, Arunan, can you ask your question?
Yes, Ned, this is Arunan here. Because I get your point that the symmetry does not allow this term. And
yes,
as Sanjay was asking you some time ago, in general, the symmetric stretch is lower than asymmetric stretch. But what is confusing me here is that the difference when omega is approximately equal to omega s, you have some energy flow back and forth, even though this term is not allowed. But in the other case, you have more chaotic. What is the reason for this difference? Even though both terms are not allowed physically, and the second term is physically not possible, can you explain the difference between these two behavior?
what it says basically is that if you have these two coupled oscillators and you pick a realistic coupling term, then as you have said, this term would not be around.
Yeah.
And then it tells you that, okay, this term, you know, this term isn't there either.
That's right, yeah.
And so
No, I'm just
for a
looking at the
realistic system of two stretches, you would never see a Fermi resonance. So that's what it just tells you, that for a realistic system of two coupled oscillators where they're both stretches, and the way I've done it, and then they're equivalent oscillators, you never see a Fermi resonance. And that's why in CO2, which you would look at this model, it has nothing to do with the two stretches. The famous Fermi resonance in CO2 is the symmetric stretch coupled to two quanta in the bend.
Bending, yeah.
So this, and that's the reason I switched to this model, because I wanted to have this coupling term, and I couldn't get it in the original one.
Mm-hmm. Okay, carry on.
Now, people said, what does this have to do with chaos theory? And I said they'd have to ask Sir Hari that question. And that's because one of the things I said at the beginning is that in realistic systems, energy flows back and forth on this particular curve. I also said that in realistic systems, as energy flows, the frequency changes. And so this would never be this curve would never be a straight line, because the frequency is changing. So you get curvatures in these things. And then it gets possible for various different lines, for different resonances intersect. And the master of the universe on these kinds of things is Srihari, who really thinks hard about these channels and molecules that open up due to resonances. And when you get multiple channels happening, where multiple lines of energy flow, and you're trying to compare the differences between quantum and classical mechanics, really interesting things happen. But all of that is well beyond the limit or the boundaries of what I'm trying to set up today. I just want you to know that you have an expert who could really, answer any possible questions you might have about these systems. Right. Eric Heller is the one who really told spectroscopists about this intimate connection between time-dependent dynamics and the spectrum. Now, Rick liked to do everything with Gaussian wave packets, and that has its limitations. But basically, if you have a Gaussian wave packet, the idea is if you start off with a Gaussian wave packet, at least for some short period of time, that wave packet will move through space, and that wave function basically will stay reasonably localized. That's his viewpoint. And so basically his picture of spectroscopy is you do a Frank-Condon progression. And so this is an excited electronic surface that I'm showing you. And I'm doing an excitation. This is a saddle point right here. So I could have harmonic oscillator motion in this direction, but in the saddle point, I can move off in this direction, or I can move off in this direction. So the wave packet, basically in his simple view, will move back and forth, back and forth. And that picture is here. Here's the initial wave packet. There's the wave packet some time later. There it is much later. You can see it starting to leak off. This is probability is starting to leak off into this side wells here. And then at some point later, the wave packet returns. Since the spectra is related to how an initial state overlaps with itself at some later point in time, this point of return is absolutely critical, because that point of return is the only way you get information about the fact that there is frequency in this particular degree of freedom. Because this time scale right here, this t, is the thing that gives this spacing between all the lines in the spectrum. So in a Fourier transform, when you see a return like this, and then maybe another smaller return at some time later, those returns are what give you a low resolution spectrum. And so the information encoded, everything you need to know, no matter how complex this is, it can speak them associative, no matter how big the molecule is, if you excite a state and it has some way of returning, then you will get interesting information in your spectrum. That was a really important point that he did. So when you think about that probability flow, think about probability flow here. If you start here and the probability flows in this direction and never comes back, basically you won't know anything about the timescales involved in this experiment, other than this very initial, this short timescale where this one has a great overlap and it has no overlap. That's that very short timescale delta. And that leads to this very broad spectral. So a broad spectrum is just a result of short time dynamics where a wave packet moves away from itself. But the recurrence that happens at some longer time is the thing that gives you all of the interesting detail. If this were bound and you kept evolving this, eventually all the eigenstates would be revealed. So Martin Kwok was one of the very first people to do this. He really wanted to think about energy flows through polyads. And he's looking at a CH stretch. And one of the beauties of you have a CH stretch, and it can have a Fermi resonance. There's this just the right kind of couplings that come into play. In other words, as you stretch that CH bond, the force constant, or the bending frequency tends to decrease. And so you get this kind of coupling. And what he's able to do, because the CH stretch can be modeled as a Morse oscillator, what he can do is he keeps putting more and more energy in the CH stretch, and he's changing its frequency. And eventually, by the time he gets up to about having 5 quanta in a symmetric stretch, you finally get a state that's really beautiful in a 2-to-1 resonance with these bend states. And so this is a lot like that spectra that I showed you, that simple model one, except you got one extra line, but you just get these peaks. And this is the experiment. So the important thing that he did when he first did this is he realized that you had these anharmonicities. And that's that one I showed you from the Morse oscillator, that the CH stretch frequency depends on its energy. And he's looking at energy flow between this particular state. These are called polyads. And he knew that the key coupling had to be linear in the symmetric stretch and quadratic in the bend. So this passes the smell test, that it's physically possible and has the right symmetry. Then what he did, these were early days, when you write down the Hamiltonian in a harmonic oscillator basis, the diagonal terms in this Hamiltonian are just the energies of the zero order state here, and here, and here, and here, assuming Morse oscillators. And then because of this term, this state is coupled to this state. And that causes a coupling term, H12. And there's a very simple expression based on doing those matrix elements, the linear term for the symmetric stretch and the quadratic term, raising and lowering operators. We know these expressions, so we have very simple expressions for these terms. So he got this very simple matrix, and he was able to vary this particular term until he was beautifully able to map out this particular spectrum. And he could do it for NP equal 5, 6, and 7. And then, because he knew about the connection between spectra and probability flow, he was able to talk about how he was able to see energy going through very rapid energy flow in polyatomic molecules.
I think Ned, that's the question. I think Shubho Mitra.
Yes.
Shubho. Yeah.
Shubho, please.
My question is regarding the previous slide. Can you just show me the previous slide?
This one?
Yeah, in this, yes, sir. Fine. Yeah, in this temporal part, like this is a population kind of thing, like a phi of phi t. The recurrence of this population after time t. So my question is, why this population is decaying after recurring? Like, is it it is decaying, like after time t it is decaying? Yeah? So my question is, why it is decaying?
Okay, if I understand your question, one of the things that's happening in this particular case, because of the saddle point nature right here, what happens is the wave packet keeps leaking off in this direction. And so classically, you would start a trajectory. If you do it perfectly like this, it would always go back and forth. But if you start a trajectory that's not perfect, it's going to go over and then come back and then go over, and that trajectory will fall apart. So this is actually a photodissociation experiment where the molecule, it could vibrate a couple times in this direction, but as it's doing that, probability is leaking out into these other degrees of freedom. What you could do that would be really cool.
Possible.
Say that again?
Okay. So physically, it is not possible to get the recurrence back in full amplitude, same amplitude, right? I mean, this is for my potential energy surfaces gets it's actually gets an harmonic in the excited state. So this thing happens for that. Like normally, physically, that is not possible to have the same amplitude back. Is it so?
I think what you're saying is, if this is bound, then the probability always has to come back. It always has to come back. And then, so at long time scale.
Yeah, like normal harmonic oscillator thing.
But basically, so at long time scale, you could imagine you'd get some small recurrences, and those recurrences would manifest themselves as little fine structure about these bigger peaks. Yeah, so this is a case where there's no recurrences, but in the case that I showed you here, if I stopped my Fourier, if I just looked up to here and stopped, basically this probability would decay and go off to 0. But it does recur, and in fact, this is the infinite time limit. And so, once you've looked at this for infinitely long, you know all the Fourier components exactly, and you get these delta function sticks. What's interesting is in many molecules, in most molecules, the whole, we have thousands of states. This is something I'll get to. We have thousands of states, and it's true here. There's thousands and thousands and thousands of states in these molecules. And the probability might come back in this particular case on some very long time scale. But basically, once that energy leaves the CH stretch and the CH bend and flows into this part of the molecule, it might take a very long time for all of that energy to just flow back into this particular degree of freedom. So it's not surprising that you get a spectra that you can't really resolve. You get these peaks that are hard to see. But if he was a great experimentalist and in infinite amounts of time, this thing would turn into, you'd see eigenstates. Molecule have eigenstates, and you'd see tons of lines here, and tons of lines here, and tons of lines here. It's just you'd have to look at a very long time scale. So time scales become absolutely critical when you're thinking about spectroscopy, especially in big molecules.
Thank you, Ned. Yeah, Shubho, is that okay?
Yeah. Yes, sir. Fine. Thank you.
Okay. Here's the simplest picture. I stole this from Fleming. The idea in spectroscopy is that a lot of times there is some bright state. For Martin Quack, he was a great experimentalist. He still is, and he knew how to put lots of excitation into a CH stretch. And then he thought about, okay, I know that for energy to flow, it's going to flow to the energetically nearby states. And I want to think about carefully what kinds of couplings are going to allow this state to couple to these nearby states. And so he was thinking, I know cubic couplings are more important than maybe quartic or quintic. You expect the lowest order terms to become important first. And so he said, moving beyond the harmonic oscillator, I'm going to think about cubic terms. I'm going to look for states nearby in energy that have this cubic coupling. And then he set up that Hamiltonian that I showed you on the previous transparency, and he diagonalized it. And once he diagonalized it, he was able to figure out the intensities of all these lines. And basically, each of these lines represents an eigenstate. And the red line represents the component of the initial bright state in that eigenstate. And then if you get a spectrum that looks like this. this is basically a buildup of the kind of thing you learn in like bonding in HF, where you have two states that mix and you get simple two-state problem with. This is would be a good point for me to stop, or I could continue. What do you?
Yeah, I think if you want to sort of take a pause here and take questions, that will be great, because I think you have sufficient amount of time for discussion, 15 minutes maybe. We can have some questions, and maybe from this point on, you can pick up for the next talk, I guess, right?
Okay.
Right, Ned, what do you think? You feel this?
I think that's good, because
okay.
What I'm going to do here is I'm going to take a paper from 2020.
Yeah.
And we're going to apply the ideas that we've learned so far to understand how Jerry Line solved this problem.
Yes. Yeah, sure, absolutely. I think there are already raised hands. First of all, I would like to invite Jayashree for asking the question.
Hi, Ned.
Hi.
So one of the things I was wondering if you can sort of comment generally is, sort of when does the anharmonicity really become important, right? So if you're working with large molecules, typically, you can work with normal modes as long as you're trying to look at some vibronic spectrum, for instance, and you're typically trying to understand some broad features of the spectrum and so on. But so when would you really invoke anharmonicity in terms of modeling, right? So this is something my students also ask, and it's not, I guess, an answer, but do you want to?
The typical thing that happens is
like energy scales, maybe also,
somebody does a Gaussian calculation, and they do the normal modes, and they predict a spectrum, and then they compare it to what they've measured in the laboratory.
Mm-hmm.
And Gaussian's so good that basically it gets the positions of the lines. Typically, it gets them pretty good. And then the question is, do you see exponent lines?
Sure.
And when is it that happens? And there are no real simple rules that I know to answer that question. I think it's a really tricky question.
And I guess it depends on the size of the system, of course.
It depends sensitively on the size of the system. And Brooks Pate did some amazing experiments, very high resolution experiments. And basically he found that when the density of states are on the order of like 10 per wave number, every system he's looked at, the energy tends to be chaotic. Energy is flowing randomly throughout the molecule. And so as soon as you move to molecules like the one you're looking at here, or slightly, this one even, in all these molecules, if you look closely enough, the energy flow is random throughout all the molecules. But so that's not the right question to ask. The right question to ask is, are there going to be timescales that will allow me to look at key interactions that are strong enough so that energy could flow in a small region of the molecule and I still get recurrences? And if I could do that, those are probably going to be to some big coupling or more important coupling, some anharmonic cubic. And that tends to be, for certain molecules, it tends to be fairly ubiquitous that you get these kinds of resonances that allow you to look in other states and allow you to interpret spectra. And I've made my whole career basically is experimentalists coming to me, they measure some spectra, they say, I ran Gaussian and it's not what I expected, what's going on? And then I have to go, I do these tricks that I've been telling you about today, and I just go in and try to figure out what are the important couplings, do they exist?
Right.
And so the rule of thumb is you always start with the cubic terms because they're obviously the most important.
Yeah, because you could still work in the sort of harmonic picture and introduce couplings between the harmonic terms, right? So that is something you can do, as a first step, and then or you could go to the Morse oscillator kind of picture where you have the anharmonic terms in there, right, which are that is for the individual modes. So sometimes it doesn't even seem necessary, right? So sometimes the couplings are important to get the signatures that they see in experiment, or sort of the anharmonicity here could be of different types in some way.
Oh yeah, I think, for example, the
Yeah.
two stretches that I showed you at the beginning,
Correct.
the reason people like local modes so much for that kind of system is you could see that there were no low order Fermi resonances in that particular system. They're not physically possible. And so basically resonances tend to be very small. And so that's in the local representation. So you just stay there.
Mm-hmm.
But people spend a lot of time, one of the interesting things about this field is, as opposed to electronic structure theory, where you don't get to pick your coordinate system per se. You just have Cartesian coordinates for all these electrons. And the beauty of this is you write your code and then it works for every single molecule. And if you're looking at real molecules, you know that, especially if you get to slightly higher energies, the motions of atoms are coupled to each other. A larger excitation, a chemical reaction, is always involving a concerted motion of your molecule. And when that happens, you can choose coordinates that reduce the couplings. And so you have an incredible flexibility in this field for picking clever sets of coordinates where something that looked like a Fermi coupling that was really important suddenly vanishes when you pick the right set of coordinates.
Right. Yeah, I remember choosing coordinates.
Yeah. So this field has a huge history of doing that. Interestingly, when you get to bigger molecules, I think the trend for what funding trends and whatnot, people are moving to much bigger molecules, and they'd spend less time trying to come up with clever sets of coordinates.
Yeah.
Okay.
Thanks.
Thanks, Ned. There are 3 questions. One coming first from Arunan, then Srihari, and then Ravindra Venkatramani.
This Arunan here, this is more of a response to Jayasree's question also. I thought when she was asking about when unharmonicity would be essential, I thought Ned may say a one-word answer always. Honestly, I have been working with mostly small molecules. I don't know of a molecule where it is not needed. But when you go to big molecules, there are so many modes, Jayasree.
Yeah.
I get a lot of papers in which they do harmonic calculations, put the experimental frequency, calculated frequency, and draw a correlation curve with 0.999 coefficient. But I can only laugh at them. See, the experiment may not show you the evidence for anharmonicity. It's always there. It's just a comment. And one other thing I would like to say, recently I found in water, of course you don't call them Fermi resonances, there are anharmonic resonances between symmetric and asymmetric stretches. And that's caused confusion with the hydrogen bond. Often we expect hydrogen bond to shift the frequencies. When you go to overtone, at times the shift happens because of the resonances. So this is leading to a lot of confusion. I am done. I will let Ned answer.
Yeah, thank you. Thank you, Aruna.
Yeah, I agree with everything you say. I think that's right on.
Okay. Srihari?
Yeah, hi Ned. Sort of nice to listen to you sort of really ramping it up.
Try to explain.
Yes, it was wonderful. Just this question, going back to this historical thing about, you said the Heller's basic idea that you had the time domain spectroscopy into the autocorrelation function, then connecting it to the spectrum as a Fourier transform. Of course, there's this sort of 2 ends of this extreme thing. I mean, you have total time domain information or total frequency domain information. Of course, I always thought that the most interesting bit about how this energy flow in this molecule accesses large regions of potential energy surface is that what time which resonance comes in and goes out. So in some sense, I guess, although this is a nice picture, time domain, and then you have the energy or frequency domain, there must be intermediate domains, right? Where you get kind of within the uncertainty principle sort of joint information about the time and frequency, in the sense that how this sort of broad spectra gets filled in. So do you have anything to say about that? I mean, have people really worried much about that in some sense, or is it always just these two limits?
No, that's it's a really interesting question. And, we never really excite Gaussians when we're doing these electronic transitions. And, one of the ways you can get around this and try to look in between cases is by tailoring your lasers to look at windows, much smaller frequency windows.
Right.
And so if you can, if you imagine on some time scale, some spectra is evolving, the Heller picture is, in the sense that it has everything, in the sense that it allows you to look at all time scales.
Right.
But over lots of time scales, as you keep looking at longer and longer times, nothing is happening. So you don't really learn anything over many time scales. And so it's basically, I think the interesting thing is, are there interesting time scales over which suddenly you're seeing new spectral features?
Correct.
And the answer to that question depends on the energy at which you're asking the question.
Sure.
So you might start to see the spectra starting to resolve itself at lower energy much earlier than you would at a higher energy.
Mm-hmm. Mm-hmm.
So all the information is sort of encoded in the Heller picture. You can't do his calculations with his Gaussians because they're not reasonable. But if one could, and look at all these timescales, I think you would get lots of information.
Right. Particularly
with the caveat is you never know what's happening when the wave packet's moved from its initial place. The wave packet moves away, all this really fascinating stuff is happening, but you're not seeing it. And so, where you would want to really step up is thinking about, is there some other window you can open up with a different kind of excitation to see what's happening when the wave packet's not overlapping its initial state? His picture shows you how blind you are, essentially.
Right. In fact, I was about to say that in the multidimensional spectroscopy is where you really want this hybrid representation.
That's right. That's where it would be really cool. Yeah.
Yeah. Okay, great. Thanks, Ned.
Sure.
We are always looking for those kinds of, I guess, correlations in doing multidimensional, I guess.
Yeah.
Right. So, and it's hard to sometimes work with all sorts of, you can make multidimensional experiments more complex by adding all sorts of frequency and time domains. But the problem is it just becomes expensive time-wise, even for an experimentalist. So.
Yeah, that's right. But you're designing these laser pulses to very specific
absolutely. Yeah.
It's all about the initial condition.
Right. I think here, this is where I would probably borrow sort of from what Ned said, is that the kind of work that Ned does, actually, this is the interesting bit, that if you know the right basis, you kind of know the interesting couplings and modes, and that ought to suggest what sort of extra frequencies you want to introduce experimentally or probe the regions.
Right.
That's the feedback.
Yeah, absolutely.
Without this information, you're sort of really searching in the dark.
In the dark, right?
Literally.
Yeah. Thanks, Shriri. Ravindra Venkatramani, you had a question? Ravi, are you here?
I think you're on mute, Ravi.
Hello.
Yeah, hi, Ravi.
I can hear you now.
Yeah, looks like my microphone is not working if headphone is plugged in. Anyways, so Ned, thanks for the extremely instructive talk, actually, with the simulations. I just wanted to get a sense of, how you prepare your initial states for your simulation, and ultimately, how do you assess thermal equilibration? Is this a problem in general?
Which was the last information, the coupling information?
Thermal equilibration.
Thermal equilibration, the approach to thermal equilibration.
all of the molecules that I'll talk about pretty much next time will all thermally equilibrate. And even in the gas phase, they thermally equilibrate. But the timescales at which they do it, unfortunately, are not accessible to the experiment. And again, because the way one has these experiments, one can excite. This is the first part of your question. You excite something,
Yeah.
and then the molecule, the energy, that's like think of this complex phase space. You've come in and you've put an initial packet somewhere in that phase space. And then when that packet moves away, your spectroscopy doesn't tell you anything. It's a simple absorption spectroscopy. You just don't know. And so one of my favorite experimentalists is Dana Delott. And what Dana Delott does is he's thinking about energy flow in molecules, and he's doing it in liquids, and so they definitely reach equilibrium. And he does things like anti-Stokes spectroscopy, and he's sitting there looking at populations at all these different modes. And so then he gets to do this multidimensional spectroscopy, essentially, where he excites something, but he can look at populations in normal modes and look at how they come to equilibrium. Now, in the gas phase, that's really hard because we don't have the signal to noise. But in the liquid, you do have the signal to noise, and you could think about, and Beeman knows all about this, you could really start to probe the populations and look at how you come to equilibrium. In the gas phase spectroscopy, that's much tougher because of the signal to noise and the fact that with simple absorption, once you leave where you started, you're only looking in a very small window. So you can't do that. Did that address what you were asking?
Yes, sort of. I was sort of looking at the specifics of, let's say you take your very simple models that you showed right in the beginning, right, with your anharmonicities of a particular type with x1, x2 square type anharmonicities. So I would imagine, like, if your states are not resonant, for example, the energy flow would not be optimal, and it would take a long time for that system to achieve equipartition, for example. Right, and if you take a large number of these states, then wouldn't assessing equipartition itself be a challenge actually in these systems, in the simulations, not in the experiments, in the simulations itself?
And this is an intriguing question, and so lots of times, it is incredibly challenging. And so you could imagine a molecule that you take some reasonably big molecule, and then you don't find any of these 2-to-1 resonances. They never quite work.
Right.
So then basically people stop studying that because at the resolution at which they can do the experiment, they see one peak. But if they're like Brooks Pate, and they can do stunningly high resolution spectroscopy, they actually can go in and start to see tons and tons of little lines in their spectrum. And that's a nightmare to do. And so for example, if you're trying to understand the CH stretch in methanol, basically when you look at the eigenstates, you see a spectra where all the energetic, if you just look at the density of states, basically everything has some oscillator string. And that's almost an impossible thing to try to model, because you're looking, when you get to that very high resolution, basically what you're having to get that right, you have to have the long-term dynamics right. And it's really hard to get the long-term dynamics right because it depends on everything. So if you really want to get all those little lines, you have to get the long-time dynamics. You would have to get the, you would be describing the equal energy flowing throughout this big molecule if that happened. And that is super hard for all the reasons you're talking about. So people tend to say, well, we can't do that problem. But we still can look at the short time dynamics and learn interesting things because we're looking at the localized couplings, and that's often what you care about is short time energy flow in these systems. So you hit the nail on the head when you say that looks hard, and that is hard, yeah.
Okay. So there is one question from Krishna Priya in the chat box and one question from Vishal, and then we will sort of conclude the session. So Krishna Priya, could you actually unmute yourself and ask the question? Krishna Priya?
Yes. Okay. So this is about the high. So this is about the energy flow in the state space. So I'm not very familiar with this. So please let me know if my question is not making any sense. So you have explained how the path in this state space wouldn't be specifically set one, but could dynamically evolve as change as the system evolves. So in that case, for a big enough system where
Let me go back to this picture so you can
mixing is strong enough.
This one here, right?
Yeah. Yes. So if the mixing is strong enough for a big enough system, what would keep the energy flow in sort of keep it from leading into a total chaos? How would it?
Total chaos, she says.
Okay. Okay. I'm not sure about my terminology. My question is if it evolves as the energy flow happens in the system as the time progresses, how would you know exactly how this the flow pattern would be in the state space, or that would keep changing?
I'm not sure I can quite answer that, but let me try. One of the leading papers in this field is by a guy named Chirikov. And he recognized that what I'm drawing, the blue line through those dots is a resonance. And for my particular system, I only had that cubic tone. But in real systems, as energy flows, frequencies change. And so you might have a perfect resonance that causes energy to flow, but as the energy flows, you move out of resonance. And so you could imagine that there will be a range of states over which you can have this flow take place. So in a real system, maybe you are perfectly in resonance. Maybe you're perfectly in resonance right here. My buttons, right? Maybe you're perfectly in resonance, like for these two states are perfectly in resonance, but maybe this one would be tuned out of resonance because it's not a straight line, it's a curved line. And so you are forced to localize as energy flow here because of the fact that as you move along this line, the frequencies of your modes are changing. And so people have figured out ways to map out classically how far you can move along these lines in these important resonances. And then they can draw another resonance and they can figure out how far you can move along those lines. And I'm only showing you one resonance, but if you have more than several resonances, the question is, can they start to overlap? So when you get multiple resonances, life gets complex. Another way of thinking about it that's slightly different is, in this particular problem, if you have this resonance, you basically have lost a constant of motion. Initially, you had two constants of motion. Basically, you had the energy in this mode and the energy in this mode. And then if you have this strong resonance, you now have, you've lost a constant of motion, and you only have, all you know is that you're now constrained to fly on this particular path. But again, it's multiple resonances and understanding basically based on the strength of the coupling and how that energy mismatch changes as you move along the line. That allows you to come up in theories with how far you can travel along those lines. Again, Sir Hari's the world expert on this. And he builds these resonant Hamiltonians that have these specific terms, and he looks at how far you can move along those lines, and he looks what happens when they intersect, and he really understands this.
Okay.
So he's a good person to ask.
Now that Ned has put me on the spot, I mean, I'll just sort of interject. I'll tell the Krishnapriya, okay, we can probably have a chat off at some point, but you're partly true. And what Ned said is things do get very complicated when you go beyond this sort of single resonance. But sort of, you've asked, wouldn't that lead to total chaos? Actually, it doesn't. It doesn't. That's what makes molecules incredibly interesting, even when they are dissociating. So it turns out, so it's based on two things. One is molecules are not just bag of atoms, right? So there's a locality to their coupling. So even when molecules are breaking, even if it has hundreds of vibrational modes, not all 100 vibrational modes are participating. There's only a handful of them. Okay, so that's one way to think that it's not going to be total chaos. But what is interesting is there is chaos, but it's what I would call a local chaos or a stable chaos. It's not a chaos in the sense of all hell breaks loose, but it's a chaos in the sense that it is a very interesting thing that channels energy in the right way into the reactive mode or modes that are going to fall apart. But you need chaos for that, but not the kind of chaos as in the English straight dictionary language.
Yeah, sure.
So the short answer is there are very beautiful patterns, even when you extend this basic picture that Ned has now for a single resonance, when you have a whole bunch of them and lots of degrees of freedom. In fact, it actually gets amazingly complex, but also something that one can actually understand. Yeah, kind of this picture, but I will not try to explain this picture here at all at this moment. But you do get this really. So, for example, in this picture, that bright yellow ring you're seeing is actually something that's called as a junction. So things are chaotic over there. They're also stable. They hang in there for a long enough time for interesting energy to sort of accumulate into the reactive degrees of freedom. And that's what seemingly happens when molecules are climbing up to the transition state. And as they come closer, as they keep coming closer and closer to transition state, fewer and fewer modes actually start to dictate terms to the molecule. And that's the most amazing fact that I think even experimentally people now know. So yeah, I mean, that's just sort of might even be a cryptic answer, but then yeah, perhaps you can send me an email and I can, or we can chat over Zoom these days. That's very popular. So I can tell you.
Okay. That would be great. Thank you. Thank you so much.
Thank you, Ned, and thank you, Srihari, as well. I will want to ask Vishal. Vishal, could you actually wait for your question in the second talk, because we are running a little bit late, and I want to take one YouTube question. Vishal, can you unmute yourself? Is that okay? Is that going to work for you? Vishal?
Okay. It's okay.
Is it possible that we take the first thing in the next talk? Is that okay with you?
So my question is very too much small. So I have a curiosity is that when we are talking of this 2D molecule, the distribution is too much poise. But when we are talking the 3D and multi-dimensional molecule, that system become too much chaotic. But for stimulation purpose, we will take just here, we will take K1 to 2 x1 and x2 whole square. It is for that stimulation purpose, or we are taking some another term? Yes.
Is that question clear to you, Ned?
Not quite.
Vishal, are you talking about going from a simple model to a very complex molecular system, a three-dimensional connected
So
model,
here the
ball-and-stick model.
with the most potential. Here with the most potential, we are taking only the term K122. We have some another term also like K123 and K141. We are taking only particular this one because we have stimulated in that way. So that.
Thank you for introducing that, and this will be the subject of the next talk.
Okay.
Where when we have a complex molecule like this, you have to come up and figure out what terms you want to include. So I will start off addressing that question at the beginning of my next talk.
Perfect, Vishal. We'll wait for the second talk.
Okay,
I'll take one. Thank you, Vishal, for the question. I'll take one question from YouTube. Anushtup Chakravarti is asking, you said depending on the coupling of normal modes are not enough. My question is why this is so. Normal modes are just a new coordinate system which should span the whole space.
Okay, that is a correct question, and so it's basically terminology. In the sense that the normal modes span the space, we could always use them to represent everything and set up a basis set up a Hamiltonian in a normal mode representation, and that works, except when there's singularities due to various motions. But you could, for everything I'm talking about, the normal mode as a basis set is fantastic. But to use the simple normal mode as a description without including the cubic and quartic terms isn't enough. So my statement was really quite simple, that you have to include the off-diagonal elements in the Hamiltonian and diagonalize them.
Right. Cool. Very nice. Thanks, Ned. That was a very, very nice answer to end with. And we would like to thank Ned, all of us. Let's just unmute your audio and have a big round of applause. It's just unfortunate that the Zoom meetings don't give you that physical feel that we have enjoyed.
No, they don't.
but going by the questions, I think people have. So
it was exciting. It was certainly exciting.
Okay, great.
Tomorrow talk. Okay.
Yes, we look forward to tomorrow's talk, and then have I hope you had breakfast, but have a break.
Okay, I'll go have a cup of coffee.
Yeah, thank you very much for sticking around for almost 1 hour 45 minutes. Yeah, thank you.
Okay, see you tomorrow.
See you later.
Thank you all for joining in.
Thank you.
Yeah. Bye, Jerry. Bye.
Bye. See you.
Yeah. Bye, Jayashree.